Greetings. I'd like to introduce forces using the PhET simulation Forces in Motion. So you can see I'm on the PhET page here, and there's a newer version of Forces in Motion Basic, which uses HTML5, is programmed in HTML5. I actually want to go with the older one, which you need to have selected Java by ChirpJ in order to access that. If I don't have that one selected, notice it goes away. And these run in the browser. They're not quite as fancy as the HTML5 versions. So you click on that, and I click on the run in the browser. And so this is going to be a very qualitative, and it's just going to basically look at the relationship between force, mass, and frictional force. So looking at frictional forces. When it loads up, you can see there are a bunch of tabs. The HTML5 programs have blocks at the bottom that you pick, a little bit more interesting to look at. So first, we're just going to start with the introduction. And we've got a box here, or a crate, and the crate is 100 kilograms. And the coefficient of kinetic friction between the crate and the ground is 0.3. The coefficient of static friction is 0.5. For some reason, they just have it starting at -6. That's certainly fine. And we can see the different force vectors. When the block is just sitting there, there's F sub g, that's the gravitational pull of the Earth on the box. F sub n is nicknamed the normal force, that's the contact push of the ground on the box. And when the box is sitting stationary on a flat surface, those two forces are equal to each other, equal in strength and in completely opposite directions. Now, and we could also look at the sum of the forces here. And notice the sum of the forces is 0. There's no arrow. It almost looks like I didn't click anything. That's because these two arrows are the same length. If I push on this, so not me, but me, my proxy, that wooden stick figure, I push on this a little bit. So notice I'm pushing with about 45 newtons of force. We've got the little arrows there. And as I push harder and harder, those arrows get bigger and bigger. Notice and again, the little stick figure, but I'll claim it's me, is pushing. So notice the two arrows. So F sub little f, that's the frictional force. F sub a is the applied force. So as I increase the applied force, F sub a is getting bigger, but F sub f is getting larger at the same rate. So those two are equal to each other, and there's no sum, or the sum of the forces is 0. There's no net force. So as I keep pushing, notice the applied force is getting larger. So first off, this is interesting because you can apply a force to something. And just because you apply a force doesn't mean it's going to move. That's one important point. Another important point, so we've got two important points. The frictional force is not just a fixed number. Oops, and look, when I go in the opposite direction, same sort of thing happens. So here, the frictional force is 57 newtons because it opposes the applied force. Here, the frictional force is 309 newtons because it opposes the applied force. So as I increase this, the applied force keeps getting bigger and bigger. The frictional force keeps getting bigger and bigger. But notice, once I reached about 500 newtons, we had a sum, we had a net force. So the applied force kept getting bigger and bigger, but once I reached about 500 newtons, then the box started to accelerate. So we can quickly do that again, and I won't talk about all this gibberish because we'll just focus on, some of the forces. So net force, keep pushing. And now there is a net force. So notice in that case, when I was pushing, the applied force was larger than the frictional force, and the box was accelerating. Notice when I stopped pushing, the applied force went in the opposite direction. So I'll talk you through that. So the force keeps getting bigger and bigger. Finally, and watch what happens when I reach 500. Watch what happens to the relationship between the applied force and the frictional force, and then the sum force. We got to click that. So and it speeds up. When I stopped pushing, the frictional force didn't change length, was still pointing to the left, and notice that the box then slowed down. When the net force or the sum of the forces is pointing to the left, the acceleration is to the left. When the net force or the sum of the forces is to the right, the acceleration is to the right. So it's accelerating to the right, and then I stop the applied force. Now it is accelerating to the left. Accelerating to the left doesn't mean moving to the left. Something that's moving to the right and accelerating to the left is slowing down. So notice that. Well, we're going to try this again, and then we can change some things. So I think I said most of the things I wanted to say there. Yeah, let's go to the friction tab then, and then we can change some things around a little bit. Surprisingly enough, I was looking back because I didn't think we could. We could not change the mass, but here we can change the mass, even though it's labeled the friction tab. We're not. Yeah, okay, we will change the coefficient of friction. But so notice what happens when I have a 100 kilogram applied force. Once it reaches about 500 newtons, that is when it starts to move. So I'm going to change the mass here to 150 kilograms. What do you think will happen when I apply a force? So I apply a little force, no difference. As I increase the applied force, when do you think the cart will start to accelerate? At 500 newtons, before 500 newtons, or after 500 newtons? Well, let's try it. So we'll keep going, keep going, keep going. Oh, I'm at 500 newtons, and the applied force and the frictional force are still the same. Now I'm clearly over 500 newtons. So I increased the mass by 50% from 100 to 150 kilograms. So think about what I might need for the applied force. All right, I got to about 750 newtons, and now we have acceleration. When I increased the mass by 50%, the box was stationary. It wasn't until I applied a force of 750. So when the frictional force got to 750, and then I pushed that extra newton to 751, that's when the box started accelerating. And notice 750 is 50% greater than 500. And you could toy around with some other things as well. So let's go with 50 kilograms. Notice that I didn't point this out before, notice that the gravitational pull of the Earth, so F sub g, is smaller. When it was a lot smaller than 750, 750 is bigger than 500. So notice that arrow changed, F sub g, and F sub m, the normal force arrow, changed as well. Now we're going to do an applied force. So a tiny applied force, not a big deal. I've increased the mass by 50% from the initial mass. And when I applied the force up until about 250 newtons, it was stationary. Once I reached 250 newtons, the frictional force reached 250 newtons. When I pushed that extra newton, then the frictional force maxed out and the box started accelerating. I'll go back up to 100 newtons, I'm sorry, 100 kilograms again. And this time I'm going to decrease the static friction to looks like I can't do incremental. I can't do anything in 100ths, so we'll just go to 0.2. And I'm going to lower the static friction or the kinetic friction here as well. So now I've taken the static friction coefficient from 0.5 to 0.2. So let's see what happens. Well, it doesn't make things go away. I push with a little force and it is not accelerating. And now I got to about 200. I moved a little bit too quickly, but somewhere around 250, you could probably figure out the exact number. The frictional force, the applied force, when it reached a certain amount in the 200s, then the frictional force could not get any larger than that, and the box started to accelerate. Notice when I stop pushing, the applied force goes away. There's still that same frictional force to the left, and then the box stops and the frictional force goes away. So you could use this simulation to look at the relationship between the frictional force and the normal force, for example. So the normal force is the same with if the box is 100 kilograms and the static friction is 0.5, or the box is 100 kilograms and the static friction is 0.2, the normal force stays the same, but the frictional force changed. So you could use this simulation to derive a relationship between the normal force and the frictional force, for example. Let's try one more. And notice the gravity here. So we're on the Earth. I'm going to change to the moon. Notice some things that are different. The mass of the box is the same. I'm actually going to go, oh, that's weird. I reset all, but it did not reset these numbers here. So I'm going to go back to the very beginning, where the static coefficient of friction is 0.5, the coefficient of kinetic friction is 0.3. Box 100 kilograms. The moon, actually, that's just to remind you. So we go to Earth, and notice, just to remind us what happens. At about 500, the box starts to accelerate, and the friction arrow is that length. Now I'm going to go to the moon, keeping the coefficients of friction the same. The mass of the box is the same. And notice that the gravity is a lot smaller on the moon, so the weight of the box is a lot smaller. F sub g is a smaller arrow, and thus F sub n is a smaller arrow as well. So let's see about applied force. So even though we're on the moon, we apply a tiny force, still the box doesn't start to accelerate. Now, not even 100 newtons, we've got the box to start accelerating. So notice that frictional force is tiny. I stop pushing. We have the small frictional force, but since there is friction, the box eventually slows down to a stop, and then the frictional force arrow goes to 0. Just a quick overview of some of those force concepts dealing with friction and the relationship between gravity, mass, normal force, frictional force. Thanks.